So let me share my screen and then we will get started. Perfect. Hello. Thank you for coming and listening. So welcome to our statistical thinking for decision making. Today we will be discovering the one-way and two-way ANOVA. The content of our presentation. So first of all, I will introduce the topic and outline the objective of our presentation. I will define critical context, concepts related to the one-way ANOVA and two-way ANOVA. These two tools or methodologies share in common their procedures, the F-values, and the statistical significance interpretation with very minor differences. Furthermore, we will go through the application of a real-life example where we will discover exactly how to apply. In this case, the data we have selected work well with the two-way ANOVA. Let's get started. So in this session, what we would like to show is how to apply the analysis of variance, which is commonly called ANOVA. ANOVA is a statistical tool for decision-making, business decision-making particularly. These methodologies, most of the time, what we do is we analyze the means of different groups that we try to compare, as well as the variability within and between groups. So what we will learn during this presentation, we will have a couple of features that I have listed here. For example, we will outline the difference between one-way ANOVA and two-way ANOVA. We will determine exactly, as I said before, the means difference between two groups. We will also produce the graph to show the variation and the residual after computing or after performing the regression within the methodology. Now, here is the definition and the conceptual framework. So within the ANOVA methodologies, we have two branches. One is two-way ANOVA. They have many things in common, some minor differences. Particularly in the one-way ANOVA on the left side, we will compare the means of more than two groups, generally more than two groups, because if we compare two groups, it's equivalent to the t-test, in fact. So we have independent variables, which are categorical, and we have one dependent variable, which is continuous. We will be using hypotheses to make the decisions, and the hypothesis on the mean. On the two-ways ANOVA, so we will compare the means as well as the interactions. So within the group, you have, for example, two categories of attributes, grade, shape. You would like to know whether the shape and the grade influence certain dependent variable individually or when combined. So this is called interaction. And we will also test the hypothesis similarly to the one-way ANOVA. The only difference here is we will test the hypothesis on the interaction as well. Definitely, we will have to make a business decision. So when we do these kind of analysis, it's to make a business decision in the end. So the one-way ANOVA follows a certain amount of assumptions, or certain number of assumptions, which, for example, reflect the independence of the sample. The response variable should be normally distributed across To meet this, for example, we need a large sample to have a normal distribution. We might meet it with a large sample, but in fact, we need to make sure that the data are normally distributed. The population variance are approximately equal, and that is called homogeneity of variances. And we also make sure, or we should also make sure that the dependent variable is continuous. Next, we will have to use certain hypotheses to making assumption on our data and trying to analyze the data to either prove the hypothesis or reject them. So the hypothesis usually used in the one-way ANOVA is there is no difference between the group, but the means are equal. And the alternative is all means are different. They are not equal. So the one-way ANOVA also used the F-test statistic, which in fact is a ratio which calculates the variability between the group and divided by the variability within the group. So the output for most of the software is as follows. And for this presentation, I have specifically used the Minitab. So the output looks like this. And most, let's say, statistical book also show this type of output. So in here, we have between group factor analysis, where we look at the p-value, we look at the f value, we look at the degree of freedom, we look at the sum square, and the MS. The MS, in fact, is this part divided by the degree of freedom. So between group, as you can see, we use k-1. Within group, we will use n, which is the total sample size minus k, number of groups. So explanation are here on the right side. On the right side. And then the total will be, in terms of degree of freedom, n-1. Total sample size, -1. So the p-value is computed based on this value. Next, we have two possible interpretations. First, we need to locate our p-value. And second, we need to set the significance level for our process. So the significance level will vary depending on each type of process. Some people might use 0.1, other people might use 0.05. From the purpose of this, we will be using 0.05. So if the p-value is less than 0.05, we will be rejecting the null hypothesis. The null hypothesis, remember, it is all means are equal. If the p-value, on the other hand, is above, we will say that there are not much evidence to reject the null hypothesis. We will not say the null hypothesis is wrong. We will say there are not much evidence. Two-way ANOVA. It's the continuity of one-way ANOVA. The only difference, as I said, are the assumptions and let's say the interaction effect. So the goal here is first to establish the differences between the means and then the interaction between the categories. So here is the real life example I have selected, in which we would like to understand if there is any interaction between the shape of the material and the grade of the material on the heat loss. So as you can see by definition here, the dependent variable is the amount of heat loss per unit length. And the independent variable would be the shape of the material as well as the grade of the material. The shape of the material, we have identified three categories or three levels. We will say the round, the rectangular, and the triangular. And the grade would have also three levels that we call, or three grades: steel, stainless, and alloy. Now, the procedure, we need to assume and make sure that our assumption hold true before we move forward. So 6 assumptions are critically important for the two-way ANOVA. 1, the dependent variable should be continuous. For example, the height, you can measure it in inches, the temperature in Celsius, degrees Celsius. And then the second assumption will be the independent variables should each consist of 2 or more categorical, like we have seen steel, stainless, alloy. And from the shape, we have seen the round, rectangular, and triangular. The third assumption will be the independence of the observation. Independence would avoid bias. We need all data to be randomly distributed. The second set of assumption is related to the nature of the data. And here, we need to ensure, for example, that we don't have outliers in the data. And the third assumption, or the fifth one, the value, the dependent variable should be normally distributed for each combination of the group of the 2 independent variables. And the last assumption will be there must be homogeneity of variance. And that can be verified using some, let's say, statistical software. For example, the methodology homogeneity of variance can let you understand very quickly whether the data follows the homogeneity of variance. Now, here is our real-life example. We have the data here. On the left side, the heat loss, which is in watt per meter. And our variables, categorical, grade, and shape. And the grade had 3 levels: alloy, stainless, and steel. The shape also had 3 levels, we would say triangular, rectangular, and round. So we will be evaluating the impact or the effect of each one of these on the heat loss and the interaction between the 2, if any. Now, this is the problem. A manager is interested to understand whether or not there are differences in heat release based on the material grade and the shape. So the dependent variable will be the heat release in watt per meter, as we have seen on the table. And each categorical will be having 3 levels that we will be assessing. So the hypothesis formulation, as you can see, 3 factors, we will have 3 pairs of hypotheses. The first one will be for the material grade. There are no differences on the mean in terms of the heat release. And then the alternative will be all the means are different. This is related to the grade. The second hypothesis, which is similar to this one, should be placed on the shape, equality of mean. And then the alternative will be not identical. And the last one will be on the interactions. I will say there are no interactions between the material and the shape. And the alternative, there are interactions. So now we will determine whether the main effect and interaction effect are statistically significant. So If the p-value is above 0.05, our significance level, the effect is not statistically significant. On the contrary, if the p-value is below, then the effect for the term is statistically significant. So the interpretation should be similar to the one-way ANOVA, but we have to be careful here that we have the interaction effect. That is why when we look at the statistical significance of one element, we have also to cross-check the statistical significance of the interaction. So now recall our hypothesis here, and then these are the results that we will try to interpret. From the analysis of variance point of view, we see that the grade had a p-value of 0.2, which is above our significance level. We saw that the shape had a p-value of 0, which is below our significance level, and the interaction had the p-value of 0.6, which is above our significance level. So out of these, we saw that the shape had an effect on the heat release, and that the grade did not, and that based on this combination, there was no interaction between these two variables. We have also, for this, we will interpret it later on the next slide. We have individual coefficient here where we can see the alloy, which is having high p-value, the stainless, the rectangular shape 0.56 on the second last column. And then we have the alloys interaction with the rectangular, which gives 0.509, and so on and so on. So the grade and shape combination or interaction have provided no significance, statistically speaking. And here we have tried to outline the regression equation. One thing which is important to interpret here is when we look at the constant, which is here, it shows a very low p-value. That means for our two categories, three grades and the shape, there is a kind of intercept at 128 with a very high statistical significance. So now we want to determine the main effect and interaction effect, whether they are statistically significant. There are various interpretations have place here. For example, the p-value of the shape was 0.0, which is below the significance level. So it contributes to the heat release. And the p-value of the grade was 0.2, which was not statistically significant. Shape and grade, as we discussed before, they are not statistically significant. And we also saw that the round, although it was statistically significant, when we combine it with other shape, we did not see any statistical significance. So there was no interaction, for example, with the stainless or with the alloy. We also saw that the p-value for the alloy and stainless grade were above the significance level. So we can see each individual p-value here and make a statistical comment and decision accordingly. Now, it's also important to assess the means, the combination of means, and compare each shape with each other, compare each grade with each other. So, for example, here we can see that the round shape stands out with 132 in terms of heat release, whereas the other shape were about 127 and 121 below. So we can see from the business decision point of view that the shape may create the thermal unbalance should the manager fail to isolate the system. So when you use this shape, you need to make sure that you isolate your process or your system to release less energy or exchange less energy. But it can happen that this shape is cheap to procure. So that is why a manager might need to do some economic calculation or analyze the opportunity cost, whether to use that shape and save some money, but by injecting some energy, or we need to go to a different shape, for example, the rectangular, which releases less energy. So we need to do some calculation to make that decision. And then we need to determine how well our model fits the data. For our ANOVA, two-way ANOVA in this case fits the data. To do this, we need to analyze the S, which is here. It has to be as minimal as possible, which shows that there is a less residual between the fitted, the predicted value and the individual value. We also need to check that the R square explain most of the variability, which is, let's say, identified in our process. In this case, our R square was 7846, which is quite consistent. And the error adjusted square, it's incorporated and it will vary with the number of predictors in the model. If you are comparing two models, for example, when you inject one predictor, you analyze the output, you will see which model gives you a better output by evaluating the R square level. And the R square predicted, it shows you the predictability. Whenever you are giving a business decision, for example, you can check this to say that, yes, I'm confident with the level of predictability. In this case, it was not calculated because potentially it indicated the low predictability potential. Now, here, this is a different way to present the residuals. Generally, these needs to be displayed on a random session. But in this case, we can see some kind of cluster here, which shows non-random distribution, I would say. We can see also that there are no outliers. The data are, let's say, scattered between -5 to 4 in terms of residual numbers. And finally, we can see that in this straight line where we evaluate the normal distribution or the normality test, most data are around the line in both ways. And there are not much outliers that we can identify in this situation. So with this, I would say thank you very much for listening. I hope we will be having to run through other different models. It was very interesting for me to go through this course and also very interesting to run this presentation. Thank you and see you next. Bye. So,